Next up, for day 6 of class, we will be dealing with pure substances. A pure substance has a consistent chemical composition. As an example, pure water is made purely out of H2O molecules. There are no impurities of any kind present. This, though, doesn't mean that it can only be one type of molecule. For instance, we could also have pure seawater made up of H2O and NaCl. But one condition of these mixtures is that it must be homogeneous to be considered a pure substance. A lot of data is known about pure substances, so we often approximate substances as pure substances as long as they are close enough. As you probably know, matter can exist in any one of 4 phases. The 3 most common ones are solids, liquids, and gases, with the 4th being a plasma, but we won't be dealing with those in this class. Intermolecular bonds are strongest in solids and weakest in gases. Solids have their molecules arranged in a repeating lattice pattern. Could be a few different options for this as well. These molecules vibrate, and those vibrations get larger as the temperature increases. If these oscillations are large enough to break these lattice bonds, the substance turns into a liquid. For liquids, the molecular spacing is similar to that of the solid phase, but they are no longer bound to the neighboring molecules. This distance also tends to increase with temperature until the substance becomes a gas. In the gas phase, the molecules are completely separated and move randomly. This is the highest energy state of matter, not including the plasma phase, which again, we're not going to deal with in this class. Going through this process from solid to gas, we can start with a solid, then as energy is added, the solid melts and becomes a liquid. At this point, the liquid is called a compressed liquid or a subcooled liquid. For water, this would be between 0 and 100 degrees Celsius, assuming standard atmospheric pressure. When the water reaches 100 degrees, it is then called a saturated liquid, which is this point right here. This is when boiling or evaporating begins. Any energy added now does not actually increase the temperature of the substance, but rather goes into the phase change from liquid to gas. The substance remains in the saturated mixture phase as the liquid becomes gas. At the moment when all the liquid has changed into the gas phase, the substance is then called a saturated vapor. So that is this point right here. So during the entire boiling phase, the substance is called saturated and will exist in some combination of liquid and gas forms while the temperature remains constant. This would be 100 degrees for water. As more energy is added, the vapor will then begin to increase in temperature. The substance is then called a superheated vapor. The temperature at which boiling occurs is highly dependent upon the pressure. This temperature is called the saturation temperature. Remember that this temperature is when the substance will exist in both the liquid and vapor phases. This value will change for different temperatures. Similarly, we can define a saturation pressure, which is the pressure at which the substance will be saturated for a given temperature. The saturation pressure of water at various temperatures are shown in this table over here to the right. Note that the value at 100 degrees Celsius is atmospheric pressure, as we know. Tables such as this also exist for the saturation temperature at various pressures, as well as saturation tables for many other substances. Some of them can be found in the appendices of the textbook. In addition to the saturation tables, there are also liquid vapor saturation curves, such as the one shown down here. These relate the saturation temperature and pressure for any substance. These are basically just the numbers in the previous table plotted in a 2-dimensional graph. In terms of the actual boiling or melting processes, they take a large amount of energy. These are called latent heats. Latent heat of fusion is the energy required to go from solid to liquid or vice versa, and latent heat of vaporization to go from liquid to gas phase. Just like saturation pressure, these latent heats can also depend on the temperature at which these phase changes occur. The properties of the substance over the entire spectrum of the phases can be found in property diagrams. These are usually presented in 2-dimensional graphs relating 2 out of the 3 state properties of temperature, pressure, and specific volume. Here are some examples. This first one on the left, having a bunch of curves relating temperature and specific volume for several values of pressure. Note that this line here corresponds to roughly atmospheric pressure, of 101 kilopascals. And this is the same curve we just saw a few slides ago. This graph, though, has other lines for other pressures as well. Other ones have what is called a saturation line. This is split into two parts, saturated liquid on the left and saturated vapor on the right. So this is my saturated liquid line. This is my saturated vapor line, separated by this critical point. Everywhere between the two will be a saturated mixture. So everything under this curve in this region here will be saturated, some liquid, some gas, at a specified temperature. These basically come from the transition points of the previous graph. So if we take all these points and connect them with a line, we get this new line here. Many of them actually combine these two graphs. So basically this whole graph and this whole graph all on the same graph. They're going to have lots of lines on them, as you can imagine. We're going to actually see some of those as part of some examples in class. And then finally, this last graph on the right is an example of a graph with different set of variables, in this case, pressure and specific volume. A few more details on the graphs we just saw. You may have noticed at the intersection of the two saturation curves, designated as the critical point at the top, this is defined to be where the saturated liquid and saturated vapor states are the same. This also defines quantities called the critical temperature, pressure, and specific volume, denoted T sub Cr, P sub Cr, and nu sub Cr. Above this point, there is no distinct phase change or boiling process. We know the region between the lines is a saturated mixture. To the left of the saturated liquid line is the compressed liquid phase, while to the right of the saturated vapor line is the superheated vapor phase. Here are some more examples of PV diagrams. They're similar to the TV diagrams seen previously. Here we see the states of the matter drawn on the curves as well. The triple line defines where the substance can exist in all three phases. On a PT diagram, the triple line is a single point called the triple point. Here's an example of a PT diagram. These are also called phase diagrams. As you can see, the phases of the substance are also marked on the diagram. The lines here define the melting, vaporization, or sublimation processes. Sublimation being the process of going directly from the solid phase to the vapor phase, or the other way around, such as CO2 or dry ice. This only occurs below the triple point, as seen on the diagram. One final point of interest is the critical point at the end of the vaporization line. Again, beyond this, there is no difference between the liquid and vapor phases. As I mentioned previously, these property diagrams relate the three quantities of pressure, temperature, and specific volume. We saw some graphs relating 2 out of the 3. The advantage of these is that they are easier to draw in 2 dimensions, but the downside is that they only relate 2 out of the 3 variables. There are also 3-dimensional property diagrams called PVT surfaces. Here, all 3 variables can be related, but they are not that easy to draw or read since they are 3-dimensional surfaces. We will generally stick to the 2-dimensional versions of them in this class. I should also mention that there is a distinction between the words of gas and vapor. I tend to use the two interchangeably, but officially, a gas refers to a substance that is far from the liquid phase, while vapor implies that the gas is near the liquid phase. Again, not too important which terms used in this class, but good to know. Another option, if you don't like these property graphs, is property tables. This is the same data, but in tabular form as opposed to graphical form. These tables contain the values of temperatures, pressures, and specific volumes for various conditions, as well as some other quantities such as internal energy, along with some others we will see later. Some of the ones we will be using quite a bit in this class include table A4 on page 888 of the textbook for SI units, or table A4E on page 938 for US units. These usually have separate tables for the various phases. For example, A4 and A5 are for saturated water, while A6 is for superheated water vapor, and A7 is for compressed liquid water. These are the property tables posted on the Canvas course website. One of those additional parameters I mentioned that is included in the tables is the enthalpy. This is defined as a combination of the internal energy and pressure times volume. So H equals U plus P times V, or in per unit mass form, little h equals little u plus P times nu. An example of the table, like A4 for a saturated substance, is shown over here. For a given temperature, we see the saturation pressure. This must be the pressure for the substance to be in the saturated state at the given temperature, along with values of a specific volume. Note that two values are shown here, nu F and nu G. Subscript F is the value for a saturated liquid, while subscript G is the value for a saturated vapor. The value of a saturated mixture can be found using these two values. We will see how to do this in a minute. There's also a third column, not shown here, called nu sub Fg. This is simply the difference between the two previous values. In other words, nu Fg equals nu G minus nu F. As we will see, this is useful for some calculations. The columns for the specific internal energy and enthalpy are similar, with three similar columns, one for liquids, subscript F, one for vapors, subscript G, and the difference between the two, subscript Fg. In the case of enthalpy, the value of H sub Fg is called the enthalpy of vaporization and is equivalent to the latent heat of vaporization. When a substance is saturated, it can exist in a combination of both the liquid and vapor phases. The amount of the substance that exists in each phase is an important quantity. The ratio of the mass of the substance in the vapor phase to the total mass of the substance is called the quality of the mixture. So a quality of 1 or 100% means that the entire mass exists in the form of vapor, and therefore corresponds to a saturated vapor, while 0 or 0% means there is no vapor, it is all liquid, and therefore a saturated liquid. The quality is denoted by X, and we can calculate it via this formula here, where X equals mg over mg plus mf, where mg is the mass of the substance in the vapor phase, while mf is the mass of the liquid phase. Note quality is only defined for the saturated state. Nothing else is a combination of both liquid and gas phases. Instead of dealing with the masses of the two phases, we usually more so deal with the specific volumes. This is more useful since nu is part of the tables and graphs in the property diagrams. So we can use this along with the definition of specific volume, volume divided by mass, and the subscripts for the liquid and vapor phases to have the second equation for the quality, X equals nu average minus nu F all over nu Fg. So the quality is equal to the overall specific volume of the substance, total volume over total mass, which is easy to calculate, minus the specific volume in the liquid phase, nu F, which we can find in the table, divided by the difference, nu Fg, which can also be found in the table. This is an easier process if the masses of each individual phase are unknown. Once the quality is known, we can then calculate values for internal energy and enthalpy. Again, the values for these quantities in both the liquid and vapor phases are given in the table, along with the differences. So there are two ways to calculate these quantities for a given value of the quality X. Either U average equals 1 minus X times UF plus X times UG, based on the definition of the quality X, or U average equals UF plus X times UFG, and similar for the enthalpies. In a sense, the saturated state is probably the hardest to deal with. The other states are easier since they only involve one phase. Temperature and pressure data can be found straight from tables for the superheated vapor state, such as A6 for water. Similarly, data for compressed liquids can be found, such as in table A7 for water. Compressed liquids are also sometimes treated as saturated liquids. This is made possible due to the smaller dependence of liquids on pressure. So as long as the pressure is not very high or very low, it can be approximated as the saturation pressure, and the saturated liquid values can be used. This is a decent approximation for everything except enthalpy, which does depend heavily on pressure based on its definition. One last note is that both internal energy and therefore enthalpy can be set to 0 arbitrarily. It is only ever the changes in these two quantities that is important. So different tables may actually have different values for these quantities. However, the difference between two states should be the same. What this means is that it's not a good idea to get the value of one state from one table and the value from a second state from a separate table, as they might be using different reference states, where the values for U and H are 0. So bottom line is, to be safe, get all the values you need from the same table or set of tables. And finally, here's the last slide for this video. As usual, giving you an example to try to work through before class. Feel free to ask any questions you may have later in class. Hope to see you there.